Hi everyone. I wanted to post a screencast helping out with the homework since there were a good number of students who were absent on Friday, which I understand it being the Friday before a break. So the homework is 13 and then 3 from 14 from the end of the book. So in this post, I'm going to talk about the examples we went over in class on Friday. So this is specifically geared towards the people who were not there. So I'm going to show you how I would want you to approach 13A and C. So all ravens are black and Jones ate 5 pies. So the thing of kerns that I have up here is these are the lambda expressions for the quantifiers, right? For the generalized quantifiers. So the example in 13 is all ravens are black, which is the same lambda expression as every. Okay. So here I'll show you, and this is very similar. So the example all ravens are black is very similar to every dog barked. All right. So here is the example. Let me zoom in a little bit. Make this bigger. Okay. So what you do, so here I even have the lambda expression for every is the same as all because the set relation of every and all is the same. All right. So all ravens are black. You need to draw the syntactic tree for it. I wrote out down here the lambda expression for every, which is the same thing. It's the same thing as all, right? It's right there. So I just copied it over. I used a different variable for the G part. So if you think about what this means, it's that every is looking for two predicates, so two one-place predicates. So that's what a set relation is, right? It's a relationship between two predicates. So if you think of, like all dogs barked, which is the example that she has in the book, the set of things that are dogs is a subset of things that are barking, right? So both dogs and barked are one-place predicates. The thing that is a little bit new about this is that the quantifiers are taking all the other entities and ET type things too as arguments. So every is looking for two predicates, right? So even though we just think of it as a determiner, it's actually, if you take a second to think about it, it's a type ET because it's taking two predicates, right? So ET is a one-place predicate, and it's returning a truth value. So that's why these quantifiers are all going to be of type ET. So then so this is the denotation of every. It's the set relation. Raven is just, I have it as Z, but you could use X, whatever, it makes no difference. So I have lambda Z, raven Z. And then black is, just lambda Y, black Y. Sorry, there should be, that bracket should be closed up there. And then R is this thing that ends up being an identity operation. So it's going to take a predicate and return a predicate, all right? So the VP is going to be lambda Y, black Y, all right? So now we first compute we do function application at the NP node. So this raven predicate is going to plug in to the lambda F part. So we're going to get rid of the lambda F since it's plugged in with raven. And we have, and it's going to, so the Z is going to be replaced by an X since that's what is in the expression up here. So we have after we've plugged in raven to every, we go up to the NP level and we've lost the lambda F, right? Because that's been occupied by raven, and we have lambda G, and then the raven set, right, which has plugged in for the lambda F, which just means, hey, give me a predicate. And this is a subset of things we don't know yet because we haven't run the function application at the S node yet. We're still left with this lambda G, which just means, hey, give me a predicate. And then when we do, so and then lambda g is going to end up being the lambda expression for the VP node, right? Because that's what's going to get fed in up there, lambda y, black y. So then we just pretty straightforwardly have that the set of things that are ravens are a subset of the things that are black, right? And it doesn't matter that we have these that we have X and U. I was just modeling what she did in the book, but if you want to have X and X, that's fine. I hope that makes sense. I will now move on to 13C, Jones 8-5 pies, which is a little bit more involved. All right. We talked about this on Friday too. Okay, so the thing with this is that you're going to want to look at example 97. Here is where it starts, 92, but it goes through the whole thing. So what is important here is that when you have a quantifier or a quantified noun phrase in object position, it's going to need to move to the sentence initial position. Okay, this is just a fact of how quantifiers work in grammar. There's a lot of linguistic evidence and work showing that quantifiers raise. So even though we hear Jones 8-5 pies, that 5 pies is in object position, there's actually a lot of evidence showing that it raises to this sentence initial position at some level of representation. Okay, so here's the just the simple set representation of 5. If you use 5 as a quantifier, that means there's an overlap of two sets, an F set and a G set, and the cardinality of that overlap is 5. So the number of entities in that overlap is 5, and that's so the straight lines indicate cardinality. Okay, so this is then the lambda expression for 5, which is taken. It's the same thing as 4, just instead of 4, it's 5, and so that's the lambda expression for that. The lambda, so it's 5 pies, and so pi is lambda x pi x, okay? So something that's important though is, and this is gone over in the book, is when this NP, this object NP of 5 pies, when it moves out of its base position and into the sentence initial position, it leaves a trace behind, so it's not like it's entirely vanished. The syntax is still aware that there is some sort of object expression that started out here as a complement to the verb eat, okay? So this example that I did, Jones 8-5 pies, is based off of how Kearns ran through Jones fed every dog, and these are obviously similar sentences in that they have a NP with a generalized quantifier in object position. So, all right. So here's the lambda expression for 5. The way that she labels the trace is as this like X apostrophe thing. You can call it like X. You can see my little mark there. She has it here, right? There's the X bar. X apostrophe, whatever. It's not an X bar constituent, which is why I don't want to call it X bar, even though obviously that's what it looks like. Let's call it X prime. If I can remember to keep calling it X prime, that would be good. Okay. So the thing is, if you think about the denotation for eat, let me actually write that out because I don't have it on here. So eat, we want to say, sorry, hang on one second. Here's my little lambda. So we'd want to say that the lambda expression for eat is lambda y, lambda x, eat x, y, right? Okay, I'm sorry I don't have that on the sheet, but you know, this should be familiar from what we did with lambda expressions before, okay? So then what happens at the VP node is that you are plugging in for lambda y for the object, right? Remember for our object, lambda y, we're saturating that argument position. So where this trace is acting as a type E entity, as an NP. So we're getting rid of the lambda y, and it's lambda x eat x prime, okay? So we're taking away the position, the lambda y. So syntactically and semantically too, the object position of eat has been occupied by this x bar this x prime constituent, which is basically a syntactic trace. Then we go up to what is labeled here as the S3 node. We have these S2 and S1, which are higher. And S3, we have the lambda x marking the subject position of eat. We just plug in Jones, so we have eat j x prime, all right? So what happens now is important. This, if you look at this looks like a truth value, right? Because there's no lambdas left. This looks like a fully saturated predicate, which in a fully saturated predicate will return a truth value. But it's not a fully saturated predicate because we still have this NP of 5 pi's floating out here, and we need to get this whole thing together for the sentence to make sense. So what we do, we add this other level of this other level of structure labeled L. She discusses it in the book, so you should definitely go back and look at this. Where is it? Ugh. Well, she has this L. What we were calling it in class is lambdification or predicatization. So what it does is it takes this thing, which is an S3, and it adds a lambda expression around the x prime, okay? So basically what it does is it takes something that looks like it should return a truth value and turns it back into a one-place predicate. And the reason why this is important is because the 5 is a generalized quantifier and is going to need to be looking for these one-place predicates, because those are the arguments that these generalized quantifiers take. They take 2 one-place predicates as their arguments, all right? And so pi is the first thing that this 5 quantifier is taking, but it's going to need another one-place predicate too, and it's created by this lambdasizer, okay? So that's what's happening here, is that we create a lambda expression around the trace, okay? Because what this 5 pi's is going to be plugged in at this trace position, right? Because it's the object of eat, okay? Even though eat is not going to be the main predicate for the full sentence, because it's a generalized quantifier, it's 5 that is going to be taking eat as an argument, okay? So then what happens after we have this lambdasizer, we are left with, so the output of S2 is this lambda expression. This NP 5 pi's is similar to what we saw in the previous one, where pi's plugs into the lambda f, okay? And here I just kept it as x. I don't have it as another variable. So we have gotten rid of the lambda f because we've plugged pi in for the lambda f predicate. So we have lambda g. So we've established that the first predicate, the f predicate, is pi. So the union, the overlap of pi and something is going to be 5, but we haven't plugged in for the g predicate yet, right? And we still have it out here too, indicating that it's still, this part of 5 is unsaturated, okay? So we've saturated one of the predicate positions that 5 is looking for, but not the other one. So now though, of course, this is 5 pi's, right? But we don't know what's happening with 5 pi's. But then we combine this with the output of the S2 node, which is this lambda x expression, and we plug that in for g, and we're left with the full sentence. So S1, the top node, we're done. So the overlap of things that are pi's and that things that John ate is 5. Okay, good.